It'd be nice to have at least an f3 f ratio. That gives me a 4-inch aperture, 100 millimeter. So if I look through the ads, I don't think I'll find anything. Maybe there is something I'm not aware of a 4-inch astrograph that's f3. But there is a telephoto lens. At least I know the Canon makes a 300 millimeter f2.8 one. I might have to stop it down to f4 for it to work properly or something. But it probably turns out that I don't have any other choice. Now, what happens if I have a bigger sensor, a full-frame sensor? It looks like I will need 460, roughly half a meter focal length. For an f3, I would need something like a 6-inch astrograph. I don't think you'll find anything like that unless it's those huge telephoto lenses that sports photographers use or something. I'm not familiar, you maybe know. But it doesn't look like a good choice. So you go back to f4. F4, maybe a 4-inch refractor with those short refractors with a field compressor or something might put you in the ballpark. But then you discover that there is something called the FSQ 106 which falls between those two, and bingo, you found your scope. Now, what happens? You want to go for galaxies or something smaller, and you've got a full-frame sensor. You need a focal length of 2 meters. Well, f3. Wow. You need a scope that's
wow, a lot of money.
that's serious stuff, and I'm not sure if anyone makes a scope like that.
I'm sure they do.
Yeah, they're
20,000.
Is there something on f3 of that size?
Hyperstar.
Hyperstar. Hyperstar is f2, and I don't know. Do they make it for
not that size?
For that size, I don't think. So I don't think you'll find a match. So you have to go down, and once you go down to f4, you start to find things that are really expensive stuff. And if you give up a bit more on your speed and will decide to spend more time, then it starts to become more realistic, you know, and you start to find things. But anyway, that's the idea. I think that's how you should go about choosing an astrograph. Don't start with the diameter. That's the last thing you arrive to. And of course you consider these other things that we talked about before, you know, all the
It's interesting you put budget last.
Yeah. Well, the budget, yeah.
Nice.
The budget.
Especially when you're talking Takahashi.
The budget is when you're like here with the FSQ 106, and you probably have more than one option, and that's when the budget makes the final decision, you know, go for this one or that one. Okay. Let's move on. There's a huge number of astrographs out there. This is not the full list. I just picked out some for historic reasons and some because they are good and interesting and useful and things like that. So there's basically two categories: the refracting ones that rely on lenses only, and you've got the catadioptric ones which use both mirrors and lenses. So if we may as well get launched into it. The apochromat refractor. On itself, it's not really an astrograph, although they make them in smaller sizes of 4 or 5 inches or so. It can be made down to about f8. You can't make it any faster because the aberrations go through the roof. Apochromat just means a lens system which brings 3 different colors of light more or less to the same focus. Much better than the old achromats, which could only bring 2 colors and the rest would make a colored blur from the secondary spectrum. Now, the apochromat itself is not, as I said, it's not an astrograph because it has field curvature. Coma is corrected, but it still has a bit of astigmatism. But the main problem is field curvature. So to turn it into an astrograph, you need a field flattener. Usually it's made of 2 lenses of the same glass usually, so it doesn't have much power, it doesn't change your focal position, the focal length of the system, and this makes a quite good little astrograph in the up to, I don't know, 5-6 inches perhaps. It becomes too expensive and unpractical beyond that. I don't think there's much to say about that. So, now the next thing is the Petzval lens. The Petzval lens is not a new thing. It's almost as old as photography. When photography started, people used an achromat to produce a lens which had a bad field curvature and all that. So they had to put a tiny field stop behind it, an aperture to make the image reasonably sharp on the film. Then this Petzval guy took 2 achromats and put one behind the other somewhere here, and managed to produce a much better lens, which still had field curvature, but coma was corrected, and astigmatism, and for many, many years it became the favorite portrait lens, the Petzval portrait lens, because it's quite sharp in the middle, and then it gives this fuzzy effect away from the face of the person. So it made a good portrait lens. Then in the 1980s, telescope makers discovered the Petzval lens, and they started to make short refractors. I think they were for visual use initially. This was before CCD came into being. And they discovered that if they separated the last 2 elements of the Petzval lens and made something like this, they could even flatten the field. And then came this. In 1999, Takahashi came up with a Petzval lens called the FSQ 106, not ED, just 106, and they used 2 lenses made of crystal called fluorite in combination with some funny glass, and that became the apochromatic Petzval lens. They didn't call it that, they just called it the FSQ 106. And they combined it with some bloody clever mechanics.
Up with numbers.
Do the numbers affect the view?
And
They're backwards.
and
I do a lot of, actually, if you've ever read their catalogues, they're very baffling.
Yeah.
Oh.
Yeah. Anyway, they came up with a really nice little astrograph. It's really good. Now, the double Gauss, I don't even know how Gauss lens. How you pronounce that?
Double gas.
Gauss lens makes a really good little. A really good little astrograph. Now you probably tell me that you never heard of a Gauss lens. Maybe someone has.
Gaussian blur.
This will be tested.
They're more like photographic.
Practically all lenses, all fixed lenses made, not just after 78, this is just what I got there, some typical examples after 78, but hundreds of lenses that are based on the double Gauss lens. Usually 6 or 7 elements, except when Canon goes berserk and they put a few more in there so that they can get down to f1.
Oh, that's fixed.
Yeah,
These are fixed lenses.
these are fixed lenses, and
So zoom lenses, you just you would not be.
These are fixed lenses, and they work quite well because it's 6 elements, but at least 2 of them are paired up. So it's only 4 or 5 groups. So that makes it about 10 air to glass interfaces where the reflection problems occur. So these are not bad, and if you want to do wide angle imaging, you don't have any other choice. You have to rely on these sort of lenses. And some of them are not bad, especially if you stop them down a little bit. But I wouldn't go for this one, even it says f1. So do a bit of research.
How much does that cost?
Yeah.
Yeah, cost. That's it. That's a deposit. Yeah.
Comes with a tube.
Then-
By jelly.
Pardon?
Comes with a tube. Pay by jelly. At least pay.
Oh.
If you need a bit more focal length, then you have to rely on these sort of telephoto lenses. But I didn't end up putting in a zoom lens cross section. Just forget them. They got about twice as many lenses in there. Then this is a fixed telephoto lens.
So you wouldn't use a zoom?
I wouldn't
Not
go
choice.
near. If you can find a good telephoto lens, it's not easy, but you might be able to find something that works. Problem is that a lot of these older lenses were designed for film, and the spectral coverage for film is different than for CCD. So you might get sharp images, but you'll end up with the red ring around the brightest stars. That's because film wasn't very sensitive in the red, so they designed the lens so that it didn't need to focus red as well. So,
Do you remember, Stefan, when Kodak had, when you got prints, you had a choice of rounded corners?
yeah.
Simply because the Instamatic lenses that they'd made didn't cover the corners, so the latest and brightest was to have...
Yeah, but it's I'm talking.
Surfaces.
Yeah, but I'm talking about the color correction, the spectral correction. That even though it was a good lens for film, it may not be a good lens for CCD. Okay, and then we go to catadioptrics. Many of you probably haven't even heard of the Schmidt camera.
Yes.
But the Schmidt camera is the best astrograph known to man.
But it hasn't got a flat plane.
It has one aberration, and that aberration is the curvature of film. But when it was used, that aberration didn't matter because film could be bent. And
They used to suck it in. They used to.
Really?
Yeah.
I've got a
You used to use a
Mr.
vacuum behind it.
You
To,
can't do that, right?
don't do that with CCD.
I brought a mystery object here. You can look at it later.
Right.
Uh,
So pass it around.
you can pass it around. This is the bit that sits in the middle there. That's where the film went to. If you want to put a CCD, that's where you have to put it.
So you have to cut it out.
Now, as well as being the best optical system, it doesn't compare with anything as far as resolution goes. This is really diffraction limited over 6 degrees field when you make it at f2 or something, and you can make it down to even f1 if you want to, or f1.5. And but it's also the ugliest optical system ever made, I think.
Go to the truck.
If you
And
see-
it has other disadvantages. It's the total length of the tube is twice its focal length. Then the primary mirror is bigger than the aperture. So it's got a lot of drawbacks. Plus, now there's a lot of huge ones that were made for professional observatories, and they have converted them to CCD by putting a field flattener lens in there and the CCD camera, but they only make use of a small area of the total field. So they're not used, but they're still good with CCDs. It just don't use the full field. Okay. Now this bit here is the film holder, so you can pass it around. If you have a look, it's got a spherical thing. You open it up, you put your film in there, and you clamp it down, and away you go. Now, there are all sorts of Schmidt derivatives. The Schmidt is always based on this funny lens in the front, called a corrector plate or Schmidt plate. It's got a funny shape, but it can be made into Schmidt Cassegrains and Schmidt Newtonians and Schmidt cameras and all sorts of. Now, one of the Schmidt derivatives used as an astrograph is the right camera. I don't think anyone at present makes them.
Don Whitehead had a right 12-inch, right, and very
Oh yeah, the people used to have them. Bratislav made one too. I've got one here too. That's a right camera, the other mystery object. If you want to have a look at it later. Now, what I've got here is actually a Schmidt Newtonian, so it's shown with an eyepiece, but for a camera, of course, you put your CCD there. But what happened? It actually has a flat film, unlike the Schmidt camera. This one has a flat field. It's quite well corrected, and it's not a bad astrograph. I don't know why they don't make them. It's probably not cheap to compete with other designs. Now, this is about the corrected Newtonian. Everyone should be familiar with these because these are used extensively. There's a lot of products available out there. I'm not actually showing the scope here. The scope is to the right, the tube. You're looking down into the tube, and this is a cross section of the focuser we've got there, and that's the camera. This is your CCD camera attached to the focuser here. And what we have here is a field corrector. We've already seen a field corrector used for the apochromat. That needed a field corrector to correct the flatness of, it's called a field flattener. Now, with the Newtonian, we not only have curvature of field, we also have coma and astigmatism. So this this field corrector needs to correct for coma, needs to flatten the field and get rid of astigmatism. And the corrector that does all that is called a wind corrector. When you buy it, you don't ask for a wind corrector, though. You ask for a coma corrector. But it does more than just coma correcting. Now, it turns out the wind corrector is really, really good. Professional observatories use wind correctors on the big telescopes. And not only it works with a paraboloid, as with a Newtonian, so you take a F4 Newtonian, you whack a wind corrector in it, and you've got an astrograph. You just turn the telescope into an astrograph with it. But you can also do this with a hyperbolical primary, which is a bit different to what's in the Newtonian. And of course, you won't use the same wind corrector. It will be adjusted. All these curvatures will be recalculated to work with that mirror. But it works even better than with a parabolic corrector. And in that case, you've got a hyperbolic astrograph. And if you go to ASA, Astro Systems Austria, you'll see they've got these nice carbon tube things there, call them corrected Newtonians and hyperbolic astrographs. And that's what they are. One mirror at the back, either parabolic or hyperbolic, and a wind corrector, and they make fantastic little astrographs. And now, this is one of the newer ones. I don't know if you've heard about the Hammer wind astrograph. It has a spherical secondary. It's not like a Cassegrain. A Cassegrain has a hyperbolic, a classical Cassegrain is parabolic and hyperbolic, and then you've got the RC, which is hyperbolic and hyperbolic there. Then you've got the Dolkirchen, which is oblate spheroid and spherical there. So you've got all this family of curves that make different instruments. But with the Hammer wind, you have a hyperbolic primary, spherical secondary, and then you've got a couple of lenses here which may look like some sort of a field corrector, but it's not. This is not a field corrector. This is actually part of the system. The whole instrument is designed together. So if you take these lenses out, you don't just have a telescope. You just have a blurry focus there. So not everything that looks like a duck is a duck. It also has to walk like a duck. So this is not a corrector. It needs to. It's part of the system. Now this astrograph is quite remarkable. It can be made to large sizes and fast F ratios, and it will break the bank though. Just to prove you that they exist, I put a picture in there.
It is expensive.
I think it still does a lot.
Even if it's not an optical thing, it still looks expensive. It looks like it's out of a Formula One.
They also make ski gear.
They help the Ferrari change.
Because you've got enough holes.
I'm joking. 20 grand or something.
That's why it's so fast.
They take all those holes out.
Yeah, but back into more
It's made in
affordable,
Switzerland.
into more affordable territory here with the corrected Dolkirchen. Now, I don't think the name is right. It is because it says corrected Dolkirchen. It sounds like you take a Dolkirchen and you put in a corrector and you got a corrected Dolkirchen. It's not the case. Again, this looks like a duck, but it's not a duck because it doesn't walk like a duck. It's again part of the system, and it's really good. And it's probably one of the cheaper astrographs to make because it's got spherical secondary. This is not too hard to make. It's an oblate spheroid. It's easier to make than a parabola or not to mention hyperbola. So when you start to get something bigger, this is probably what you'll consider. Now we all heard of the RCs, the Ritchie-Chrétiens. Practically all large professional telescopes are made to this formula. The primary is hyperbolic and so is the secondary, and as a result you end up with quite well corrected film, but it has curvature. So yours is an RC, Morris?
Well, the Vixen isn't.
The Vixen.
It's,
Corrected
it's,
Newtonian?
it's closer to a correct. It's closer
Dol-
to a Dol-Kirkham.
So it's a
than
corrected
yeah.
Dol-Kirkham.
Steve Moore's got a Ritchie-Chrétien.
Yeah.
Plain way, I think.
Yeah.
Ritchie-Chrétien.
Oh yeah, yeah.
So,
Yeah.
that's all right.
Well, there's one good thing about these Ritchie-Chrétiens is that you only need a 2-lens corrector, and this time it is a corrector. It's a real duck. It walks and looks like a duck. Because if you take it out, you still have a Ritchie-Chrétien telescope. If you put it in, then you've got a Ritchie-Chrétien astrograph.
So, nice to ask, is a Ritchie-Chrétien much better than a Schmidt-Cassegrain for astrograph?
I did not even consider the Schmidt-Cassegrains, unfortunately. I think the Ritchie-Chrétien would be better. Now, of course, there's all sorts of variations on the design. You see some spot diagrams. The circle is your aberration limit, probably, I guess. Oh, Maxudovs, I don't like them.
You don't like them?
I don't like them.
Are they duck type?
They're more geese.
Is it Russian or because?
It was invented by a Russian.
But then so was the Kalishnikov.
Yeah, during World War II it was invented in 2 places, in the Netherlands and in Russia at the same time, the Maksutov system. Now this is a derivative of the Maksutov because usually the Maksutov telescope has long focal length. It's not suitable as an astrograph. A few years before film went out of fashion, these Maksutov derivatives were becoming quite popular as astrographs. And people started to, they separated like you can have the secondary mirror as an aluminized spot on that lens, and it works very nicely as a telescope. But to produce an astrograph, you need to get away with the secondary from there and make it bigger, and then you still have a bit of a curvature of field, and that could be solved very easily just by putting a simple lens in front of the film. It would flatten the film. Now with CCD cameras that's not possible anymore. You can't stick lenses right in near your sensor. So I think that's one reason the Maksudov derivatives went out of fashion. Although it is possible to bring this even further somewhere, make it really big and produce a flat field ones, but no one's making them commercially. So
The obstruction is to scale. It's quite a large obstruction, secondary.
it does, but that's another thing with astrographs. It doesn't matter. With telescopes, it it matters because the airy pattern changes. But we're not interested in airy pattern, we're interested in those little blobs to be smaller than 2 pixels, and as long as that happening, doesn't matter, it can be 80% of the, you just lose some of the light through the obstruction, but it doesn't matter for imaging. Now, perhaps I should, I don't know, I probably went on for too long, but I think I should clarify one big difference between extended objects and point objects when it comes to imaging. There is a fundamental difference. The image of a star is not actually an image. When we looked at the airy disk and diffraction pattern, that is not an image of the star. That is a diffraction pattern. It's produced by the laws of physics. If that was an image of a star, it would have to be so small that it would be vanishingly small. It's not a... So, what happens now if we have a planetary nebula, like a ring, a smoke ring with a... They tend to have a little star in the middle. So we have an extended object, then we have a star. We take two astrographs. We scale one up, so we get one twice as big. Everything, focal length is twice as big, diameter is twice as big, everything's twice as big. And we image the same planetary nebula, that little ring with a star. What do we see on our sensor? Well, we find that the ring is twice as big. But we also find that the star is not bigger because it's a diffraction pattern. It's the same size in both sides. And that makes a huge difference between extended objects and point objects. Like, your bigger scope catches 4 times as many photons, right? Because it's twice the aperture squared, you know, it's proportional. So it catches 4 times as many photons. Your little ring nebula in the focal plane is being twice as bigger, has 4 times the surface area. So 4 times the surface area with 4 times as many photons means it will have exactly the same brightness on your chip, on both in the little one and in the big ones. But that's not the case with the star, because it's the same dimension, both of them, and one has 4 times as many photons focused on that little dot than the other one. So your star gets 4 times brighter, but your nebula stays the same brightness. So this is where the difference comes in between extended objects, and people get confused completely about these things when they discuss on the internet this focal ratio myth and all that. They try to convince you that it's this way or that way. So you have to get this, these basics understood. Aperture doesn't matter, F ratio matters. See, you're going after nebula, you're not going after that star. If you were doing some photometric measurements, you know, measuring the brightness of the star, yes, you want as big aperture as you can. If you use the scope visually, you want to see stars as faint as possible. You want the biggest aperture telescope you can get. Also, visually, you adjust the focal length so that nebula gets smaller and bigger to suit the sensitivity of your eye, where the contrast, the perception is best. But with an astrograph, you don't vary the magnification. You've got your sensor size and you've got your focal length, and you, of course, you can buy yourself a set of CCD cameras with small chip, bigger chip, and use which you want, but I don't think it's a practical way of going about it. Yeah. Okay, so we got anything else? Yeah, this is yet another class of that may look like a refractor. It's got two lenses at the front. This again can be made into Cassegrain systems as well and all sorts of things. Makes good little astrographs, but this is not these lenses have little power. They just corrector lenses and they're made of the same glass. And they make a nice flat field astrograph. Again, I don't know if anyone likes any of those. But now we've just arrived into the 21st century. This is the ultimate in astrographs at the moment. It's I changed the name a little bit because you'll find them called RH astrographs, Ricardi Hondes, but it's actually, it was this German guy, Buda, that patented it, and then it was this Italian guy that started making them, and I think he comes out as winner with a name. the name has stuck, I think, now as RH, Ricardi Hondes. But yeah, anyway, it's a revolutionary design. Amazing that no one came up with this arrangement before.
So what it is about that design?
It's just nothing like anything else.
Is that a lens at the back, Steph?
We've got, I'll go through it. We've got one lens here, meniscus lens. We've got another lens here which is aluminized on the back. So it's both lens and mirror. So you can call it a Menge mirror, or we call it a mirror lens. Then you've got a spherical mirror here, and then you've got another lens here. Now, interesting thing is that all these three pieces of glass, that one, and that, are made of the same glass, same type glass. That's a requirement of the design. And you end up with a quite well-corrected field, and it can be made to about f3 in small size. There's a couple of versions of it. If you bend this lens, can be bent the other way, forward, and then you illuminize a spot on the back of it, and it becomes the secondary mirror. So you don't even need this here, but you need a group of two lenses down here somewhere. And that can be made up to about 200 millimeters and at f3. And that's what Officina Stellare, the Riccardi mod in Italy, make they call it the Veloce 200 or something. And then
Is it an economical design to manufacture?
it is.
Oh,
Look,
is it?
the bloody length is about as short as the diameter of the thing. It's the most compact design you'll ever see. And of course, all you need is a short carbon tube going from there to make it stable.
You started making one yet, Steph?
Yes, it's grown up and everything, but there's a long list of projects.
You take accepting orders.
Would you have it
I'm
by
going
next,
one.
by next meeting, perhaps?
No, I'm actually going one better. I'm making a Riccardi Hondes that has a guide scope which is also a Riccardi Hondes.
And what's the point of that, though?
Well,
Just to say
you know,
you get ready
how the hell you wanted to have a Riccardi Hondes this long and then have a guide scope that's that long riding on it? It looks silly, wouldn't it?
purely
Okay,
aesthetic.
now astrophysics in the US came out with a 12-inch version that looks like this. You know, they've got the separate secondary, and they made it f3.8. That's what Peter Ward uses. Yeah. Now, I think a couple of pictures here. Now, this is the astrophysics version. That's 3.8. And now this is
That's just,
That is.
that's astronomy porn, isn't it?
That's dreadful.
this is